Rates of change, which we've talked about before, is basically we talk on the derivative. I mean, that's what the derivative is. It measures a rate of change of some quantity compared to some other quantity. Now, when we look at the graph, basically we know this. The steeper the curve, the faster the quantity must be changing. So if I've got a graph like that, then at the point P, what can I tell? Well, I know at that point the derivative is positive. So it's saying the rate of change is positive. So in other words, that function is increasing. And we saw that in curve sketching. That was the basic idea. And then we saw if we're at a point like Q, the tangent ends up being horizontal. So there is no rate of change at that point. It's stationary. It's not doing anything. And then, of course, it comes down the other side. So we're at R. And now we have a negative slope, so it's decreasing. They're just three basic fundamental ideas. Here's the same graph. If we're moving from the point P to Q, then the slope of PQ, the secant, that would tell us the average rate of change when we went from P to Q. Okay, so that's the average rate of change. Whereas when we look at the derivative, so we're just looking at that point R, that's what we call an instantaneous rate of change. And that's probably more useful. It's like if you're driving in your car and you're speeding, which you shouldn't do, of course, but you get pulled over. And the police officer says to you, hey, do you realise what speed you were travelling? Yeah? And they book you and you go, hang on a sec, whoa. But if you average my speed from P to Q, actually I was under the speed limit. Doesn't work. They're not interested in the average rate of change, they want the instantaneous rate of change. Travel graphs then. Way back in, I don't know, year 7, year 8, you'd get a typical question like this. You've got some sort of graph, time versus distance there. So we've got a coach leaving a depot, 9 a.m, it's going on a tour. And they asked you questions like this. How long was the first stop? And you'd look at your travel graph and you go, oh, stop, I'm looking for the flat bit. And so it was 30 minutes, it went for 30 minutes. Now what you were really doing, although you didn't realise it at the time, you were looking for when that graph was stationary, when the tangent was horizontal. So when did the coach start to return to the depot? And we go, we'd look at it and say, hang on, it must have been at 1:30 because that's when the line's going back down. That's when the rate of change was negative. That's what we were looking at. Because we didn't use those terms back in year 8. How fast was the coach travelling on the return trip? And then we could work out, well, speed equals distance over time, 100 kilometres per hour. But what you're actually measuring there is the slope of that line. Calculate the average speed for the whole trip. Well, in this case, it's travelled 400 kilometres all up and divided by 6.5 hours, so 61.5 kilometres per hour. That would have been the average speed for the whole trip. Okay. But of course, back in year 8, we had to have nice blocky lines and things like that. But now we have calculus, we don't have to have blocky lines. Our travel graph can be a curve. The equation of this one there is x equals 5t, 8 minus t. So the beauty of that is, if we've got the equation of the curve, we actually don't need the graph because we can use our calculus to find the answer. But if we were to ask similar questions, if we wanted to find distance is of course the total amount travelled, we could work that out. As opposed to this thing called displacement. Those of you that do physics will realise, of course, what displacement is. But displacement's a little bit different. It's just how far are you from, well, some reference point, usually the starting point. So we said, find the height of the ball after 1 second. Well, I can substitute it into my formula I've got now. So when t equals 1, x is 35. Yeah, I could read it off the graph as well if I had an accurate graph. At what other time is the ball the same height above the ground? So when else is it 35? We would go and solve the, well, it turns out to be a quadratic equation. And we get 2 answers, t equals 1 or t equals 7. Well, we already knew t equals 1. So the other time must have been t equals 7. Notice I'm answering the question. I'm not just saying t equals 7. They've asked me at what other time. I'm telling it, oh, well, it's after 7 seconds. So I'm answering the question. Now, average velocity, which is different to average speed. Average velocity would be the change in displacement over time. So distance is speed over time, but velocity is displacement over time. And that can make a big difference. But essentially, yes, we're finding the slope of our lines, whether it be the secant or whether it be the tangent. So okay, what is the average velocity during the first second? Now that's where you've got to be careful. We think about first second, well that starts at 0 and ends at 1. So that would be the first second. Well, at those points we were at 35 and obviously the other one was 0. So we know it's 35, our units in this one, meters per second. What was the average velocity during the fifth second? So the fifth second would go from t equals 4 to t equals 5. So let's find those values. T equals 4 we get 80, t equals 5 we get 75, and we get a negative answer. But now when we're talking about motion, the negative has a different meaning. It's telling us about direction. So if it's positive, we're moving in the positive direction, which in our problem is we're going up. But if it's negative, we're going in the opposite direction, which in our problem is going down. So the plus or minus becomes very important. How do you answer it? I can say the average velocity is negative 5 meters per second. I could also say it's 5 meters per second in the negative direction or something like that. Well, what's the average velocity during the whole 8 seconds it's in the air? And this is where we get a really weird answer, because we get 0. What? So on average, it's not moving at all. But that's because we're talking about displacement and not distance. And as far as displacement is concerned, yeah, we didn't move. We started at this point. After 8 seconds, we're back at the same point. We didn't move. So the average velocity was 0. Now, average speed is the difference one. That's where we don't care about the sign, the plus or minus. It's just the actual distance that we're travelling. It's similar to when we did integration about areas where it's above the axis and below the axis. Well, when we were talking about area, we had to split it up into two things. But when we were talking about the actual integral, it was fine to do the whole bit. So it's the same sort of thing. So find the average speed during the 8 seconds. Well, now we're talking distance over time, not displacement over time. And the distance it travelled was 160. It was 80 up and 80 down. So its actual speed averaged 20 meters per second. Okay, so that's just a little intro into basic motion.